Right, we're going to realise when we're doing all these first principles videos that the procedure is actually quite cumbersome. Is there actually a formula? If we've got f of x is equal to ax to the n, is there actually a simple formula we can apply and then we can just differentiate what's known as directly, not from first principles? So let's have a look at this from first principles and see if we can come up with a formula. So we've got f of x is x to the n. So an example of that would be 7x to the 10, say. Okay, so f dash of x is the limit of h goes to 0 of f of x plus h minus f of x over h. So f dash of x is the limit as h goes to 0 of a times x plus h to the n, using function notation, minus a times x to the n, all over h. Okay, a is a common factor, it's not part of the limit because the limit is h. So what we can do, we can take the a out of the limit sign. So we've got a ln lim of h goes to 0 of x plus h to the n minus x to the n over h. If you recall, when we had like x plus h squared or x plus h cubed, we would expand this. So we can expand this one here, using the binomial theorem. So that's going to give me a lim as h goes to 0 of expanding x plus h to the n using the binomial theorem, x to the n plus nc1 x to the n minus 1 times h plus nc2 x to the minus 2 times h squared plus nc3 x to the n minus 3 h cubed. Now that's going to carry on and it will stop when we get to h to the n. So if you're not sure about that, go back and recap the binomial theorem, and then we have to take away the x squared, x to the n, all over h. Right, we've got x to the n minus x to the n, so they will cancel out. And so we've got a lim of h goes to 0. Now nc1, oh sorry, just one extra thing. There's now a common factor. Once you've removed these two, there's now a common factor of h, so we'll take that out. And nc1 we know to be n factorial over n minus 1 factorial 1 factorial. 1 factorial is 1, so we'll forget about that. So we're going to have n times n minus 1, n minus 2, all the way down to 1 here. And then we're going to have n minus 1, n minus 2, all the way down to 1 on the denominator. So they all cancel out. We just get left with an n. If you're not sure about that, try something like 4c1 or 5c1 or 2c1 and see what you get on your calculator. You'll see that it's always going to be n. So in the case of 4c1, you'll get 4. Okay, so nc1 is n, x to the n minus 1. That h is now gone. Plus nc2, x to the n minus 2 is no longer x squared, it's h. Plus nc3, x to the n minus 3, h squared, one's gone. Plus h to the n minus 1. Don't forget to close off the bracket and then close off the whole thing. Right, because n is not actually equal to 0, it's very, very close to 0, but not actually equal to 0, we can cancel. And because h is so small here and here it's even smaller and here it's even smaller, we're just going to be left with this term here, nx to the n minus 1, and we had the a up front, so we get a n x to the n minus 1. So if f of x is a x to the n, then the formula for differentiation is you bring down the power, write down the variable, and then you reduce the power by 1. So hence we've got two rules. If we're using function notation, f of x is a x to the n. F dash of x will be a n x to the n minus 1. If we use the other notation that y is equal to a x to the n, Then for the gradient function, dy by dx is the notation, and again we get the same value, a n x to the n minus 1. And the videos that follow will do some examples on these. Okay, but please bear in mind what you're doing here when you're doing this process, it's called differentiation. You're differentiating ax to the n with respect to x to get a n x to the n minus 1. And geometrically, this gives you a formula for finding the gradient at any point on this curve. To find the actual gradient at the point, you take the x coordinate and substitute it in. Okay, I hope you've understood this, and I thank you very much for watching.